Good morning and welcome back to Survey of Calculus. Normally I'd say, it's great to see you here today, but I'm standing in a classroom all by myself, wishing you were all here. Anyway, I hope you're well, and let's jump back into Chapter 4, Section 4.1. We were finding local extrema, local max and min points, high and low points on a graph relative to other points near it. And we said in order to find those local max and min points, we need critical points, which is an x value in the domain. Cannot be at an end point if we have a restricted domain, where the derivative is 0. So if we substitute that critical point into the first derivative, we get 0, or where the first derivative is undefined or does not exist. We did not talk about that before we left, so we'll go there in just a minute. Okay, so if you recall, here we have a local min, and here we have a local max, and the derivative is 0. Remember, the derivative calculates the slope of the tangent line at those 2 points, and if the slope is 0, we have a horizontal tangent line. Okay, so we're looking for those places where we have a horizontal tangent line. Here's a situation we did not necessarily talk about previously, is here I can see that I do have a horizontal tangent line, but I have no local max or min. Okay, so it's kind of like x cubed where the graph levels off. Okay, and we said at these local max and mins where our graph is changing from decreasing to increasing or vice versa. Okay, and we said we could do that first derivative test. Here, my graph does not change. It's increasing to the left of the critical point, and it's increasing to the right, where we know our first derivative is positive if it's increasing, and our first derivative is negative when it's decreasing. All right, so what about this whole idea of what's this x value that makes the derivative undefined? How does that play out? At a critical point, a value in the domain of the function that when you plug it into the first derivative, it does not produce a real number. That is because we have a vertical tangent line. Okay, and we know that vertical lines have an undefined slope. Okay, we don't see this in Math 125, if any. Okay, but it's worth bringing up. All right, so then we said, we actually talked about a first derivative test for local max and min and a second derivative test for local max and min. So we had started an example, which I hate ending in the middle, so we're going to finish it. We had started this example 3, and we said, let's use the second derivative test to classify a critical point as local max or min. But we're going to do it both. We're going to do the first derivative test as a review, and then we'll compare, make sure we get the same results with the second derivative test. Okay, so first thing we need is critical points. Anytime you're looking for a max or min, you need critical points, which requires the first derivative. Okay, so we found the first derivative, we set it equal to 0, and we solved. All right, so we found critical points of -9 and 5. So if we're doing the first derivative test, then we're trying to see if the first derivative changes its sign from positive to negative or vice versa at those values. So I have -9 and I have 5. And if you remember, we did our number line test. And what we substituted it into the values into the first derivative to see if we got positives or negatives on each of these intervals. So we chose a test value in each interval. So I'm going to choose something left of -9. So how about -10? I'm going to choose something between -9 and 5, so I like to choose 0 if I can. And I'm going to choose something out here. I'm going to choose +10. So if you want, you can make a little table like we did during class, not required, but it's kind of nice to summarize your results. Okay, so my test value is -10, 0, and 10. Okay, and the idea, remember, is to plug them into the first derivative, but it's much nicer if we use the factored form of the first derivative. Okay, so I'm going to write that up here so we can see. Oh, there it is above. Duh. Okay. Anyway, so I've written it up here. So if we plug it into each factor, we can determine if it's going to make that factor positive or negative and then multiply. So the first factor is a constant. It's always going to be 3, so it's always positive no matter what. Okay? When I put -10 in here, I get a negative. I put -10 here, I get a negative. So a positive times 2 negatives is a positive. Okay, so any number you choose on this first interval, you could choose something besides -10, should give you a positive value. Okay, if I continue plugging in 0, I get a positive, I get a negative, which leaves me with a negative. So any number in that interval produces a negative. And substitute in 10, I get a positive, I get a positive, I get a positive. Okay? All right, so that's what happens with the first derivative. All right, so what is that telling me about the graph of this function f if I was going to look at its graph? Because the first derivative is positive, I know that the function is increasing on that interval. First derivative is negative, it's decreasing, and then it's increasing. So according to the first derivative test, if it changes from increasing to decreasing, we have a local maximum. So we have a local max at -9, which is a critical point. If it changes from decreasing to increasing at a critical point, then we have a local minimum at x equals 5. Okay? If we wanted to look at the graph, we could find the ordered pairs for those points by substituting them back into the original function. We'll do that a little bit later with another example. Okay, so let's compare and see if we get the same results using the second derivative test. The second derivative test can be used to determine local max or min if, let's go back up and review, if we get a positive value or a negative value when we substitute the critical point back into the into the second derivative. Here's where it doesn't work. If we plug our critical point in the second derivative, the test is inconclusive. I don't know if it has a local max min or neither. I have to go back and I would have to use that number line. So the idea is I could go back to my original question without doing the first derivative test. I can go straight to the second derivative test and see if it will work. Okay? So second derivative test relies on the fact that we have the first derivative. All right, so the second derivative then, if I go back up here, the derivative is 6x plus 12. All right, and now we don't set it equal to 0. We just say we're going to evaluate our critical points at each of those values. So if I do f double prime of -9, so I'm going to plug my first critical point into the second derivative, and then I'm going to plug in my second critical point into the second derivative. Okay, and what do I get? If I plug -9 in here, I should get -42. The key is that it produces a negative value. So the second derivative test says if you get a negative value in the second derivative, That tells me then, remember the second derivative tells us about concavity. And if it's negative, it's telling me that the function is concave down. Okay, so at that critical point, it must be a maximum. Okay, because we know it's a point on the graph where the tangent line is horizontal. It's concave down at that point, so it has to be a max, which is, I believe, what we found with the first derivative test. Okay, so when I substitute 5 into the second derivative, I get positive 42. I got a positive value, which tells me that the function is concave up. So at that critical point, then, we know that we have a local minimum. So it's pretty sweet if you can just, if all you need to do is find out if you have local max or min. You can use the second derivative test, unless either of those would have evaluated out to be 0. All right, so here's one for you to try. So I'd like you to pause the video, and I would like you to give this a try, and then you can check and see your answer. All right, so critical points. Where the first derivative is equal to 0. So we need the first derivative. We set that equal to 0. And we solve. Remember, factoring is a big thing for solving polynomial equations. So greatest common factor is a 3 and an x. So if I factor out a 3x, I get 6 minus x as my other factor. Set each factor equal to 0, and I would get x equals 0 or x equals 6. Okay, so these are my critical points. All right, so what do we need to do? We need to use the first derivative test. So at each critical point, we would like to know if the first derivative changes its sign. Okay, so my first derivative, I like to use the factored form when doing the test. That's up to you. All right, so I've got 0 and I've got 6. And I'm going to choose a test value in each interval. I'm going to choose -3. I'm going to choose 1. And I'm going to choose 8. And I'm going to substitute those into the first derivative over here and see if I would get a positive or a negative. So when I put in -3, I get negative. When I put in 1, I get positive. When I put in 8, I get negative. Okay? So what happens here? On this interval, my function is decreasing. On this interval, it's increasing. And on this interval, it is decreasing. So what does that tell me at 0, my critical point? Changes from decreasing to increasing. We have a local minimum. And here, we have a local maximum, changes from increasing to decreasing. Okay, let's find the ordered pairs for those points. So if we're looking for points on the graph, the actual ordered pairs, then we have to find the y-coordinates of those points. So I have to put 0 back into the original function. Be careful, we've been plugging things into the derivative. Original function, because we're finding the y value of the point on the graph. So if you do that substitution, we should get 0, 0, and 6, 108.